Welcome to Monochemistry. We're going to look at some basic concepts around reaction prediction. And before we get into actual prediction here, we're going to review the 5 major types of reactions. There are lots of different types, but these are the 5 major ones that you learn about in grade 10 and continue learning about in grade 11. The 5 major ones are combination or synthesis. Either one of those is fine. Decomposition, single displacement, double displacement, and combustion. We're going to look at each one of those. We're going to look at what they kind of look like, and then we're going to learn how to predict products based on whether or not we think it's one of those 5 types of reactions. Okay, so let me show you. For a combination or synthesis type reaction, here's the general formula or what it would look like. Okay, so you have something like A plus B, which by the way are not real elements. This is just pretend. It's a model. Will give you a combination of those things, or you're putting them together, and it will give you A, B. Okay, so in other words, like 2 elements, element A plus element B, give you compound AB. 2 things added together to give you 1 thing of the combination. That's the general way, that's how you recognize them. Okay? So, let's just, for example, try a quick one like this. Say we have zinc plus sulfur. Okay? A plus B. What the heck am I going to get? Well, I'm going to get some sort of combination of those. Okay, so first of all, you have to identify the fact that this is indeed a synthesis reaction. Once you've identified that it's a synthesis, because it has 2 reactants and neither one of them are compounds, they're both elements, then you can predict that it will be this. So the final product will be zinc sulfide. Now, it just so happens that in this ionic compound, the zinc has a 2+ charge and the sulfur has a 2-. Okay, so I can just write it like that. In fact, this equation is balanced. But remember, whenever you're writing the product, whenever you're predicting the product, you have to look at the individual charges of the ions and figure out what the chemical formula is going to be. Don't forget to do that. This one just happens to work out. So is it always going to look like this? No, sometimes it might look like that, right? You get the idea. But the general idea is you have 2 things combining to give you 1 new thing, which is a combination of those 2 things that you started with. That's a combination or synthesis. A decomp is the reverse of that. So in the last example, we had A plus B yields AB. Well, in this case, we're going to start with 1 thing, a compound, and it's going to break up into its individual elements, or pieces. So this would lead us to A plus B. That is a decomp reaction. Okay, so let me give you an example here, a slightly different one. Say we had water. Now we want to break water up into its individual elements. Well, the individual elements of water are hydrogen, as you can see here, and oxygen, as you can see here. So what does that look like on the other side? Well, it looks like this. H2. Remember, hydrogen is a diatomic, which means you never write it by itself when it's alone. Here it's H2 because it's part of a compound, right? And O is by itself. Over here it's O2, so H2 and O2. Okay, now notice this is not a balanced chemical equation. However, it is a decomp. How did I know that it was a decomp? I knew it was a decomp because I started with only 1 reactant, and that 1 reactant was a compound. So it broke up into its individual elements. A single displacement reaction takes on the general characteristics of this. Watch. A plus BC yields B plus AC. It can also take on the form, if you start off with A plus BC, it could also be C plus BA. Okay, and it depends on what you're dealing with in terms of metals and nonmetals. We'll get to that in a second. Okay, so how do you identify the fact that it's a single displacement reaction? Well, you're going to have one element reacting with an ionic, and this is important, it has to be ionic, an ionic compound. Okay? So the element can either be a metal or a nonmetal. And depending on which part it is, it's going to have these different arrangements in the end. Okay? So let's try one. Let's have something like magnesium plus barium oxide. Okay, so notice I have a metal reacting with an ionic compound. That's how I know it is single displacement. And because I know it's single displacement, I can now predict the products. Magnesium is a metal, barium is a metal. They are going to switch places. So what I should end up with on the other side is barium plus magnesium oxide. Running out of space there. Okay, that would kind of take the form of this one. Now, if this reactant was a nonmetal like sulfur, then the two nonmetals would switch places, and I would end up with slightly different products. I'd end up with oxygen and magnesium sulfide. Or sorry, oxygen and barium sulfide, not magnesium. Okay, there's no magnesium if I replace it with sulfur. Okay, either way, it's a single displacement. Double displacement reactions take on the form of this. AB plus CD yields CB plus AD. Notice that I kept the first ones in the first spots and the second ones in the second spots, because these are both sets of ionic compounds. Very important to keep in mind. So here's an example. Sodium chloride, ionic compound, plus potassium iodide yields. Okay, so notice I have two ionic compounds. Right away, when I have two ionic compounds, I'm going to assume that this reaction is a double displacement reaction. So how do I predict the products? Well, we know that this and this are metals. This and this are nonmetals. So in order to write the correct products, I need to swap places. The metals need to swap places, okay? So this is going to go with this, and this is going to go with this. Okay, so I'm going to write, doesn't matter which order I write them in, I'll write sodium iodide plus potassium chloride. Okay, double displacement. Combustion reactions involve any element or substance, doesn't have to even be an element, it could be a substance, reacting with oxygen. Okay? And when you combust them, you get various products. Okay? But a combustion reaction has to have oxygen as a reactant. So if you have two reactants, one of them is oxygen, then you will definitely recognize that as being a combustion. This can also be, depending on what type of thing we're talking about here, can also be a synthesis reaction. Okay? So again, you can predict them. Here's one way to identify for sure that it's combustion. Take a look at this particular reaction. Now some people might look at this and say, okay, well you've got a compound and an element, so that's a single displacement. Unfortunately, no. This is not a single displacement because this compound here is not ionic. In order for it to be a single displacement, one of the compounds, or the compound in the reactant side, has to be ionic. It doesn't work any other way. Okay? So for this one, if it's a hydrocarbon, like this one is, hydrocarbon, plus oxygen, we're burning it, we're combusting it in oxygen, you're always going to get CO2 and H2O. Okay? The key here is, though, this. If oxygen is one of the two reactants, it's likely a combustion. Okay, but if it's combusting a hydrocarbon, then you're always going to get CO2 and H2O. If it was just something like aluminum plus oxygen, like here, then you would get aluminum oxide. So it would be like a combination reaction. So a metal plus oxygen, still combustion, but it's also a combination. So it would be Al2O3. Remember, the compound that you write over here, if it's ionic, has to be based on the charges.